Hi, welcome to your first laboratory practice at the Department of Electrical Engineering, University of Moratuwa. Alternating current circuits. Before moving on to the practical, let me ask you something. Have you ever wondered how the electric appliances in your home function? And what actually an electric current is? Most probably you may have that question. But don't worry. Through this laboratory practice, you will be given an approach to figure out answers for them. Now, let me introduce you the electric current. An electric current is a measure of the amount of electrical charge transferred per unit of time. It represents the flow of electrons through a conductive material, such as a metal wire. It is measured in amperes. As you may already know, there are two basic types of electric current flow in a circuit as direct current and alternating current. By abbreviating these terms, they are called DC and AC. In DC, the electric charge only flows in one direction, while the electric charge in AC, on the other hand, changes its direction periodically. In this laboratory session, we are going to deal with alternating current only. Now let's have a look at the real-world applications of AC, which are familiar to our day-to-day life. AC is mainly used in the industry of the transportation and production of electricity. In fact, almost every household in the world is powered by AC. Therefore, the majority of the household appliances rely on this. For example, refrigerators, washing machines, electric cookers, and the list goes on. You can find out some more appliances on your own, if you are curious about this. Apart from that, AC is also the most popular current when it comes to powering electric motors, a device that converts electric energy into mechanical energy. An induction motor can be taken as the most popular and widely used example for an AC motor. Now let's see, why do we use AC instead of DC? AC devices are efficient, simple, robust, and they require less maintenance compared to DC devices. Also, the production of AC is less expensive than the DC systems. Moreover, AC systems can easily be modified into DC type using rectifiers. In AC systems, a wide range of voltage levels can be achieved using step-up and step-down transformers. This feature is highly beneficial in power transmission over long distances, since the transmission line losses can be reduced with that. Now, let's identify some basic parameters of an AC waveform. Alternating waveform that is used with electric power is the sinusoidal waveform. A sinusoidal AC waveform having a peak value or the maximum value of A, and a frequency of F, can be represented like this. A sinusoidal waveform can be represented using phasors. Oh. What is a phasor? Don't worry, now we are going to discuss about the phasors and phasor diagrams. In simple terms, a phasor is a rotating vector. If I explain it further, it is a scaled line whose length represents an AC quantity that has both magnitude and direction, which is frozen at some point in time. This is the phasor representation of the sinusoidal waveform. Here you can see, the phasor that has a narrow head at one end, is pivoted around a fixed 0 point, known as the point of origin. The phasor is allowed to freely rotate around that point, in an anti-clockwise direction, at an angular velocity omega of 1 full revolution for every cycle. This anti-clockwise rotation of the vector is considered to be the positive rotation. So, the sinusoidal waveform is the vertical projection of that phasor rotation. For an instance, you can see now the phasor is frozen at point A, and its vertical projection corresponds to the 30 degrees point on the time axis of the sinusoidal waveform. Also, when all the phasors rotate at the same speed, for simple graphical representation, we can draw all the phasors in reference to one selected phasor, and it is called the reference phasor. Compared to this reference phasor, sometimes you will encounter leading phasors and lagging phasors. So, let me tell you, why do we need these phasor diagrams? This phasor representation is very useful when studying the voltages and currents in the three main passive elements of AC circuits, called resistors, inductors and capacitors. I'll explain them further in the upcoming part of this video. Now, let's talk about the relationship between the frequency and the rotational speed of the phasors. So, this is the basic equation representing that relationship. Here, the frequency can be taken as 50 Hz, which is the supply frequency of the national grid in our country. Now, let's try to identify the three basic passive elements of an AC circuit, and their features. First, I'm going to introduce you to the resistor. You may haven't come across a real resistor we are using for laboratory practices before. But don't worry. I'll explain you the basics of the resistor. So, this is an adjustable resistor, used in applications that require varying resistance in an electric circuit. In electrical terms, it is called a rheostat. Its resistance element can be a metal wire or ribbon, carbon or a conducting liquid depending on the application. Now, let's see how the connections are done. Here you can observe, there are three terminals as A, B, and C. If we need to use the full resistance in the circuit, how can we connect this? For that purpose, we can connect the terminal A and B, like this. But, what if we need to vary the resistance in the circuit? For that, the sliding contact comes into play, and we can connect the terminals B and C, as shown here. Then, by moving this sliding contact on the metal part, we can vary the resistance. Now you can see the symbols we use for a fixed resistor and a variable resistor in an electric circuit. Also, these are the images of the real resistors we are using in the laboratories. Now, let's try to understand the VI relationship across a resistor. If we consider the instantaneous values, we can derive this equation by applying the Ohm's law across the resistor. Also, we can derive another equation using the RMS values as well. Now, we're going to draw the phasor diagram for a pure resistor. Here, I'm going to take the current as the reference phasor. As you may already know, the voltage across a resistor is in phase with the current through it. Therefore, the current and voltage phasors will rotate together, and the sinusoidal waveform will appear like this. Alright. Hope you received some insight about the resistors. And now, we will move on to the next circuit element, which is called the inductor. In the most basic form, an inductor is nothing more than an insulated coil of wire, wound around a central core. Normally, the current flowing through the coil produces a magnetic flux around it that is proportional to this flow of electric current. These inductors slow down current surges or spikes by temporarily storing energy in an electromagnetic field, and then releasing it back into the circuit. Normally, the inductors can be categorized into three basic types, depending on their core materials as air core type, steel core type and solid ferrite core type. Also, this is the symbol we are using for an inductor in electrical circuits. Now, let's try to figure out the VI relationship across an inductor. An ideal inductor with no resistance in the coil opposes the flow of current through it by dropping the voltage directly proportional to the rate of change of current. This opposition to current change is called the reactance, rather than the resistance. Therefore, we can derive the relationship between the instantaneous voltage and current across an inductor, like this. Also, by applying the generalized form of the Ohm's law, considering the impedance of the inductor instead of the resistance, we can derive an expression for the VI relationship of RMS values as well. Okay. Now let's see how we can draw the phasor diagram for an ideal inductor. Here also I'm going to take the current as the reference phasor. As you may already know, the voltage across an ideal inductor leads current through it by 90 degrees. Therefore, the voltage phasor rotates, leading the current phasor by 90 degrees. As a result, the sinusoidal projection of that phasor rotation will also indicate a 90 degrees phase difference between voltage and current, like this. Alright. Hope you got some understanding about the inductor. So now, we are going to discuss the final passive element, which is called the capacitor. So, let me explain you what a capacitor is. A capacitor is a component that has the ability, or capacity, to store energy in the form of an electrical charge, producing a potential difference across its plates. There are different kinds of capacitors, available from very small capacitor beads used in resonance circuits, to large power factor correction capacitors. Also, these are the images of the capacitors used in our laboratories, and this is the symbol we use for a capacitor in electrical circuits. In the basic form, a capacitor consists of two or more parallel conductive plates, which are not connected or touching each other, and they are electrically separated by some kind of dielectric material, like air, wax paper, mica, ceramic, and the list goes on. Here you can see the structure of few other types of capacitors. Now, we are going to derive the VI relationship of the capacitor. By definition of the capacitance, we have an equation as Q equals C multiplied by V. If we differentiate this equation with respect to time, we can obtain the relationship between the instantaneous current through the capacitor and the instantaneous voltage across it. Here, we know by definition, a current is the rate of flow of charge. Also, we can take the capacitance as a constant. For more convenience, we can rearrange the terms by integrating both sides with respect to time. By applying the generalized form of Ohm's law, we can derive the relationship between RMS voltage and current across a capacitor. Here, the impedance of the capacitor is defined as 1 over omega C. Okay. Now let's see how we can draw the phasor diagram for an ideal capacitor. Here also, I'm going to take the current as the reference phasor. You may already know that the voltage across an ideal capacitor lags behind the current through it by 90 degrees, and it can be drawn like this. When the rotation takes place, the voltage phasor rotates keeping a 90 degrees lag behind the current phasor. Therefore, when we take its vertical projection, the sinusoidal waveform also indicates a 90 degrees phase difference between the voltage and the current. Now, the introductory part of the passive circuit elements is over. So, what should we do next? Do you have any clue? Okay, let me tell you. Now, we are going to combine the previously gathered knowledge to compose the phasor diagrams for the series RC circuit and the series RL circuit. First, let's have a look at the series RC circuit. Here, it is obvious that, since the resistor and the capacitor are connected in series, the same current flows through both. Therefore, it is fair enough to take the current phasor as the reference. As we discussed earlier, the voltage across a resistor is in phase with the current through it, while the voltage across the capacitor lags the current by 90 degrees. So now, let's draw the phasor diagram for the series RC circuit. First, I'm going to draw the current phasor I in the reference direction, and the voltage phasor VR, which is in phase with that, also can be drawn like this. Then we can draw the voltage phasor VC, which lags I by 90 degrees, in this way. Finally, we can draw the supply voltage phasor Vs, completing the phasor diagram. Here, the Vs is obtained by the phasor addition of VR and Vc. If Vs is taken as the reference, we should rotate the phasor diagram to make Vs horizontal. Similarly, we can consider the series RL circuit as well. Here also, because of the series connection, the current is common for both resistor and inductor. So, we can take the current as the reference phasor. As previously mentioned, the current I is in phase with the voltage VR, while the voltage across the inductor VL leads current by 90 degrees. So, in this case, we are going to combine these two phasor diagrams. Now, let's draw the phasor diagram for the series RL circuit. Here also, first I'm going to draw the current phasor I in the reference direction, and the voltage phasor VR, which is in phase with I, like this. Then the voltage phasor VL, which leads I by 90 degrees, can be drawn in this way. Then we can complete the phasor diagram by drawing the supply voltage phasor Vs, like this. Here also, Vs can be obtained by the phasor addition of VR and VL. Moreover, if we need to take Vs as the reference, we can simply rotate this phasor diagram to make Vs horizontal. Now, we are moving on to the final theoretical concept related to this laboratory practice. Here, we are going to calculate the inherent resistance of the inductor. Have you ever heard about this inherent resistance of an inductor? What is that? Okay, let me explain it to you. As we already know, the resistance of an ideal inductor is 0. But the practical inductors possess some resistance value, due to the inherent properties of the material they are made of. But their role is designed to be inductors, not resistors. So, their inductance value is comparatively higher than the resistance value. Now, let's see how we can calculate this inherent resistance. Here, we have taken an RL series circuit into consideration. Then we can draw an imaginary circuit by separating the inherent resistance value from the inductance. By applying the generalized form of the Ohm's law to the inductor and resistor separately, we can derive the equations 1 and 2, like this. Then, we are going to divide equation 1 by equation 2, and derive an expression for the inherent resistance of the inductor, RL. Okay, now let's draw the phasor diagram for this circuit. Here again, I'm going to take the current as the reference phasor. Now you know, VR and VRL are in phase with the current. So, we can draw them in this way. Since we have a pure inductor in this modified diagram, the voltage VL' should lead the current I by 90 degrees. Then, we can complete the diagram by taking the supply voltage Vs as the phasor addition of VR, VRL and VL'. Also, we can draw VL as the phasor addition of VRL and VL'. Now, we are going to rotate this diagram to make Vs the reference. Here, the main thing I want to highlight is, the voltages that are perpendicular to each other in the phasor diagram are not VR and VL, but the addition of VR and VRL with VL'. This is the end of the theoretical concepts behind this laboratory practice. Hope now you have some understanding of what is going on in this laboratory session. Now, it's time to move on to the practical session, conducted in the electrical laboratory. So, let's go. Before starting our practical, let's have a quick look at the circuit diagram, and try to identify the components of the apparatus. So, this is the circuit diagram we are using to connect the circuit. Now you can identify the two passive elements present in the circuit as the variable resistor and the capacitor. Apart from them, here you can observe there are three similar components as V, VR and VC. They are called voltmeters. Finally, you can identify the supply voltage and the variac, which is used to adjust the voltage values required for this laboratory practice. Okay, now, without any further delay, let's start the laboratory session. First, we will understand the series and parallel connections available in this circuit separately. If we look at the series connections, from the source terminals, we are giving supply to the variac input terminals. From the output terminals of the variac, we are giving supply to the resistor. Through the resistor, current passes to the capacitor. Then through the capacitor, we are connecting back to the variac. We are connecting all the voltmeters in parallel to the apparatus to measure the relevant voltages. When we are connecting voltmeters, depending on the measurement, we can select the range we need. Here we have 0 to 150 volts and 0 to 300 volts range. For this practical we are selecting 0 to 150 volts range. We are connecting Vs voltmeter in parallel to the voltage source in order to measure the source voltage. To measure the voltage across the capacitor, we are connecting Vc voltmeter in parallel to the capacitor. Similarly, to measure the voltage across the resistor, we are connecting VR voltmeter parallel to the resistor. In this practical, we are using full range of the resistor. To get the full range we are connecting wires to these two terminals. Before starting to take the readings, we should bring the resistor value to its maximum, then we switch on the power supply to the circuit. After that, we adjust the variac to set the source voltage to 50 volts. Now adjust the resistor position stepwise. And take the readings of VR and VC voltmeters. Make sure to keep the source voltage at 50 volts. By adjusting the resistor position, we reduce the VR meter reading by 5 volts. And note down both VR and VC meter readings. Here we demonstrated only 2 resistor positions. Likewise, you can continue the practical for few more meter readings. After taking all the readings, make sure to bring the variac to 0 position and switch off the power supply. Okay, this is the end of your first laboratory session at the Department of Electrical Engineering, and here I have prepared a table containing all the meter readings as the observations of this session. Please use them for your calculations when you are preparing your lab report. So, thank you for joining with this laboratory session, and let's meet again with your second laboratory practice at the Department of Electrical Engineering.